Welcome to the first lecture of System Software. I am your instructor, Paul Gazzillo. I'm sorry I could not be there on the first day. I am at an academic conference in Estonia, and I will be back next week at our next lecture. Just a reminder that this Thursday's lecture is canceled because of the football game. So as I said, I'm your instructor, Paul Gazzillo. And we have one graduate teaching assistant named Mesut Azdag. A little bit about me. I'm an assistant professor here, which means that in addition to teaching, part of my job is also research. And my research interests include software engineering, specifically analyzing configurable software, program analysis for security, where I specialize in side channel attacks, and also blockchain smart contracts, which is software that can be executed on a blockchain. And this is more of a side project, but my interests there are in concurrency and safety. And I'm always open to having new students work with me. If you're interested in seeing what research is like, what kind of projects you can get involved in a couple weeks, I have weekly meetings on Fridays at 3 in HEC 356. So if you're interested, come by. My teaching interests are related to these research interests. I'm interested in programming languages, program analysis, software engineering, and software security. So system software fits right into my wheelhouse. Today's lecture is going to be pretty light. We're going to talk just about why studying system software is important, what system software is. We'll talk a little bit about what the class project is, and then we'll walk through the syllabus. And the GTA will walk you through setting up some of the tooling that you'll use for this project. The utility of studying system software is that you know your tools better, become a better programmer, and satisfy curiosity about how our machines work. So in any engineering or technical discipline, knowing your tools is incredibly important. So take pilots, for instance. Pilots spend hours and hours of time in the classroom just learning physics and aerodynamics so that they can understand how their tool, the airplane, reacts in the real world. And woodworkers have a vast array of different kinds of tools for having different effects on the wood that they're working with. And this bottom picture is from the vehicle assembly building at the Kennedy Space Center nearby. And this is like the largest building by volume in the world because rockets are large. They're complicated pieces of machinery. And so the tooling used to maintain and put together these massive pieces of equipment require massive, complex tooling. And so for you as a programmer, your main tools are your language tools, your development environment. And so knowing the ins and outs of these tools will make you a better programmer. And that's another goal of this class. Something to get out of this class is how to be a better programmer. Now, when you go out into the world, and many of you will be software engineers, will be working with technology, there are tons of different frameworks, tons of different applications. Maybe you'll be programming low-level systems. Maybe you'll be doing Internet of Things programming, maybe web programming. And while all of these on the face seem like different computing technologies, they're all still computing, and they all have a lot of commonalities behind them. So by understanding the system tools that we'll go over in this class, I hope that when you encounter new system tools and new systems in the real world, that you'll have a better grasp and be able to pick these up more quickly. And lastly, and maybe most importantly, is just to satisfy curiosity. So this might be more applicable to me. I devoted my career to studying computing technology. But there's something gratifying about taking the things we work with every day, like the compiler or the operating system, and just opening the hood a little bit and seeing how they work on the inside. What is system software? System software is a pretty broad term, but we can summarize more or less what system software is with three properties. They support the operation of a computing machine. They create an environment to run application software. And they also support the development of software. We can loosely categorize them into two groups. One, we have the development environment, and this includes your editors for compilers, assemblers, linkers, debuggers, and the runtime environment for actually executing the programs that you develop. This is the operating system, loaders, dynamic linkers, libraries. Everybody knows what the editors are. It's can create and edit text files. This is how you modify and create your program source files. The compiler translates your source files into assembly code, which is a text format that mirrors the underlying machine instructions. And then your assembler translates that assembly code into object code, or the actual machine code, binary code. Linkers collect multiple object files together into a single program, and the debugger allows you to examine the state of a running program so that you can test it or debug it. For the runtime environment, we've got the operating system kernel. The operating system kernel is the lowest layer of software on your machine, and it abstracts away details of the hardware so that you as a programmer don't have to worry about whether you're programming a hard disk, whether you're using a solid state drive, whether you're using ARM or Intel. And it also mediates access to the hardware between the many programs you have running on your system. The loader takes a program off of disk and it copies it into RAM so that it can actually start running on your hardware. Libraries are reusable pieces of code that your software can link to. So for instance, when you call printf, you're actually calling into a library that some developers wrote for you to help you format your print output. And the dynamic linker allows you to load these libraries while your program is executing so that you don't have to link all of these libraries together into your program. So it allows for a much smaller piece of software. Here's a diagram that shows how most of these system software tools fit together to take your source file into a program that's running in memory on your machine. We've got your compiler, which takes the source file and converts it into assembly code. The assembler converts that assembly code into machine code or an object file. The linker combines all of these object files and any libraries that you want in your program into a single executable. The operating system is how you store this executable onto a storage medium like a solid state drive or a flash drive. And the loader works together with the operating system kernel in order to take that program off of disk, copy it into RAM, and then start executing that program at the first instruction. So this semester's project is going to be writing a compiler. We need a compiler because the source language we write in, like C is not understood or processed by your hardware. In fact, I don't know any machine in the world, any hardware that actually processes C and runs it. The compiler takes that program and translates it into the set of instructions that your hardware actually implements. And so what that means, that's why you have to first compile your program in order to get your executable. And then your executable is interpreted by the hardware itself. It takes your input, gives you your output. An interpreter, on the other hand, is kind of a software emulation of a machine. It doesn't require translating it to machine code because the machine that executes your program is the interpreter code itself. So for this entire semester, you're going to be writing a compiler. This compiler is going to be for a very stripped down version of C that I call Simple C. We're going to start with a very, very simple version of this language. And in your first project, you're going to write a complete compiler, but for a very, very simple language. And then as we go along, we're going to add new features to this language and slowly build it up to a more complete language. And this is going to be 5 projects spread out over the entire semester. Now, developing software requires being able to use system software. And so one of my ulterior motives behind this class is to expose you to real-world systems tools. And so to that end, this project is going to require you to use some system tools for building your compiler. And I've chosen prevalent industry standard tools for doing this. So you'll learn the basics of using a build system to automate the compilation of your software, so you're not just writing GCC commands every time. We're going to use make for that, make files. I'm also going to require you to use source version control. In fact, if you've looked at the homework 1 yet, your first homework is to set up your source code repository on GitHub. So GitHub provides a classroom environment. Now there's lots and lots of Git services out there like GitLab, Atlassian, Bitbucket. They're all great. I happen to pick GitHub. I happen to use it. You can even use Git, of course, without any service. Git is just a command line tool. And so you'll be tracking your changes to source code with Git and submitting your projects by pushing these changes to GitHub Classrooms. Now, to make sure that everybody has the same platform to build and run their compiler, I'm going to have you use a virtual machine running the Linux operating system. And we're going to use some widespread tools called Vagrant and VirtualBox to fire up and run this virtual machine in an easy way. And lastly, we're going to use the LLVM compiler framework, which is an industry standard compiler framework for writing compilers, and it'll make it much easier to generate binary code. So today, the Graduate Teaching Assistant will give you a tutorial on Git and starting to use your GitHub Classrooms repository. But if you look at the syllabus website, under the projects directory, there's a bunch of information and tutorials about setting up these tools. So make sure you set up GitHub Classrooms, that's homework 1 in web courses. Set up Vagrant, which is the virtual machine manager, and actually kick off your virtual machine and start using it. There's a file called Vagrant Setup in the projects directory. And also set up your local Git repository inside of the virtual machine. And today's tutorial and this file called git.md will give you some tips on doing that. If you have any questions at all, be sure to use Piazza. I've set up Piazza for this course. It's worked out well in the past. So be sure to ask your questions there. And then next week, once we start on Project Zero, we'll look at how do we actually use the LLVM framework, how we link and run the LLVM intermediate code. And if you look at project0.md in that projects directory, that will get you started on doing that. So now let's walk through the syllabus. You can find the syllabus posted on a public GitHub repository. Let's take a look first at the README. This contains the syllabus. Here we've got some information about the course personnel, including the websites and email addresses of the instructor and the teaching assistant. Note that questions will be taken on Piazza and may not be answered quickly via email. Use email for personal or registration issues. These are the office hours that we propose for the semester. 4 days a week, Monday through Thursday, 1 hour per day, 2 hours by Mesut, 2 hours by me. Also note the days on which there will not be office hours. Here's the schedule of the course. Presumably you know this already. Note that there's no lecture on Thursday, and there's no lecture on Thanksgiving. Here are the lab times and the final exam period. The location is typically in our lecture room for the final exam. Here we have the schedule for the rest of the semester. The first week will just be an overview, going over how to set up some of our tools like Git and Vagrant. Thursday, there's no lecture because of the football game. The following week, we'll talk about the operating system and get you set up with actually running LLVM so you can start on Project Zero, and we'll go over the compiler project. The week after that, we'll talk about how lexing works for the next couple of weeks. Then we'll talk about parsing and grammars. I'll give a little tutorial on recursion and some more parsing algorithms. Then we'll talk about how variables work in programming languages, and we'll actually implement it in the next couple of weeks. We'll look at structured programming and control flow and how constructs like if, while work in programming languages. And finally, we'll look at functions, and the functions will be the last project that we do, the last mandatory project. Then we'll look at a little more advanced topics in program analysis, namely optimization, control and data flow analysis. We'll look a little bit at how software security can be automated, and program analysis in general. The next semester I'll be teaching a graduate program analysis course. Some of you may be interested in that. Some of you may be interested in that because of this course. I think you need some sort of permission to take it as an undergraduate, but it's certainly possible to take that. And then for the last 2 weeks, we'll do review and have our final. Now this course will have 25 very small homework assignments, effectively 1 per lecture. Now these are very small. Don't worry, these are going to be very small homeworks. You'll have a week to do them. They will always be assigned at the end of a lecture. They should be on web courses by the end of the lecture, and they'll be due the following lecture at the beginning of the following lecture at 7:30. There are some lectures where no homework will be assigned. They are listed here, and there's no late homework permitted. But these are small assignments. They should be easy for everyone to do. They're not graded strictly. They're graded mostly for completeness. They're just to make sure you're engaging with the material and paying attention in class. The TA will take notes at every class, so if you happen to miss a class, you can find the lecture notes and slides on this repository. The projects, there are 5 mandatory projects for the course, and there is 1 and bonus projects available for you to do. And these are always due before class at 7:30, either Tuesday or Thursday, depending on the project. And there's roughly 2.5 weeks between these project due dates, so you can find the project due dates listed here. And they'll also be on web courses to remind you. Now, I have a very liberal late policy, but the final deadline for all late project submissions will be just before the final exam, Thursday, December 5th at 7:30. And this will be reflected in your GitHub classrooms as well. But keep that in mind. So for grading, 60% of the course grade will be these 5 projects. There'll be 12 points each. You will work individually on the projects. No group work or no sharing is permitted. Submission will only be via GitHub, via the classrooms on GitHub. You have 1 repository, and each of the projects will be a release. And the TA today will go over how GitHub tags works, how tags work in Git, and how they can be used for releasing code. Releases are typically in software engineering used for versioning. So version 1, version 2, these are releases, and Git has a mechanism for recording these releases. And you'll be using those for submitting your projects. The project source code should never be made public, even if it's for an interview. The repositories on GitHub Classrooms are private, and they should never be shared. And this is, according to the academic integrity policy of UCF. The projects are cumulative, so if you get behind on one project, it may hold you up for the next project. So the grading scheme is if there's no release for your project for that project, you get 0 points. If there's evidence of some amount of effort, you get 1 point. If it compiles, you get another point. And the remaining 10 points are the prorated number of test cases that you pass. So roughly half of the test cases will be public, roughly half will be secret. So we'll give you test cases in the projects directory that you can use to evaluate your project, and then write your own to make sure that your project works properly, and we'll have some secret test cases to evaluate your project with. Now, I have a very liberal late policy. You can submit your project pretty much whenever you want up until the end of the semester with small amounts of penalties with points off. You can also resubmit your project if you think that you can do a better job. You can resubmit your project, and there are instructions on how to re-tag and re-release older projects. Of course, when you submit for regrading, you lose some of the points for the late penalties, so we'll take the maximum of whatever it ends up being if you want to resubmit your project. And we'll talk a little later about how to resubmit. You'll have to notify me or the TA in order to do the resubmission so that we know about it. The late policy is that up to 2 weeks late, you get a point off, and any time past 2 weeks, there are 2 points off. And just to keep in mind, the absolute deadline for even the late projects is 7:30 on the day of the final. That should say 7:30. I will change it. 20% of your grade will be homeworks. There are 25 very brief homeworks, but the lowest 5 are dropped, and they're 1 point each. These are going to be assigned and submitted by you via web courses. And keep up with these homeworks, because these homework problems are going to be used to make the final exam. And I don't like to grade super strictly, so just try your best on these homeworks, and they're mostly graded for completeness. And 20% of the class, the remaining 20%, will be the final exam. The final exam will be roughly 2 hours. All the questions will be based on homeworks. They're open note, not open laptop, but open note. And then there's some room for discretionary points for participation. You can undertake bonus projects if you want to have a little additional challenge on top of the compiler project. You can get extra bonus points for completing these projects. There's one listed right now in the projects directory, but I can certainly give you an endless number of projects. And then we've got how the numeric grades translate into letter grades, and UCF has a policy for how letter grades translate into GPA. And the rest of the syllabus is information about the course, what the outcomes are supposed to be, what you're supposed to learn, the course materials. So the textbook for this course is not required, but it is recommended. There are some formal algorithms that we go over that this textbook has a comprehensive treatment of. So I would recommend getting the textbook, but I understand these textbooks are expensive, so you can get Guide without it, but you will miss out on some of the more formal treatments of the algorithms we go over in the class. And if you have more interested in compilers and compiler design, I've listed some supplementary textbooks, which are fantastic textbooks. If you check them out of the library or happen to find them, you can buy a digital copy online, or you want to buy a copy yourself. These are excellent books for learning about compilers. And then we have some of the core policy statements about academic integrity, plagiarism. I recommend reading these. There's information about course accessibility. So for those who require student assistive services, there's only one in-class exam, and this can be taken at student assistive services. We have notes being taken by TAs, but of course you can use student assistive services to have a note taker for you. And some more information about campus safety and deployed active duty military students. So that is the syllabus for the course. Here you will also find projects, and once we have notes and slides for the course, there will also be a notes directory. Let's take a look inside of projects. Now here, if we take a look first at the README, it gives you some background on the project, some of the tooling you need, and then links to all of the project descriptions. So let's first take a look at all of this text. So it goes a little bit into what your compiler will be doing, how it will be using the LLVM framework. It'll give you a little blurb on using the virtual machine and a link to setting up your virtual machine. Now for grading, we will be automatically grading your projects. So in order for that to happen, your compiler should be able to be built by just downloading your source code and running make. Make will automatically build the project, and we'll go over how to actually use make and how to set up make for your project. And it should be run using the Simple C program, just like it says here. So your program, your final program should be called Simple C. And it should only take a single argument, the name of the source file, a .simplec extension, and its output written to standard out should be an LLVM intermediate representation file. And we'll go into more detail over the next couple of weeks what that intermediate representation looks like. So we as the graders should be able to redirect that output using this greater than sign. This redirects the output into a file with a .ll extension. So to run the output of the compiler, and we'll go into more detail next week once we look at Project Zero, to run the output of your compiler, we will use the Clang compiler that will take your LLVM representation and turn it into a binary program that can be executed. Now, one of the hardest things to wrap your head around when making a compiler is that the compiler itself is a program. It's a special kind of program that takes source code as input and produces machine code. But keep in mind that the compiler itself is a program, and that program needs its own compilation. So as I mentioned before, to submit your project, you submit it by tagging a commit in Git, and the TA will go over today how that works. You can also look at this Git MD file for a little tutorial on the basics of using Git. So I'll let you read over this yourself and follow along with the TA today. And I've also listed out what tags each project should have, Project 0, Project 1, etc. And now we come to the project descriptions. So the grammar overview and the lexical specification, we'll go over those in a little bit more detail over the next few weeks. But if we click on each one of these project descriptions, each project will go over the objectives, the learning objectives, the skills you will need, which we'll cover in lectures and labs. There will be a grammar description of the language, which we'll go over more next week. This just describes all possible programs that the source code could look like. An example, here's an example of the program. Project 0 is very simple. It's only a list of print statements with arithmetic operations. And then a description of what the target language should look like. And so this is getting into what LLVM intermediate representation looks like, and we will cover that next week. And finally, it'll tell you, this project description will tell you how to get started using LLVM, compiling it, and running your LLVM output. So in the next coming weeks, as we get to the later projects, these project descriptions will be filled out further. And at the bottom, you have a links to all of the important documents for setting up your tooling. Vagrant, Git, test cases. So the test cases folder will have some scripts for running test cases. It'll have a folder for each project for the test cases that should pass. And that's it for the syllabus. So over the next coming weeks, we'll go into more detail about the projects. There will be class notes posted sometime after each lecture. And I look forward to teaching you all and getting to meet you all next week. And now the TA will go over the tooling. So have a good rest of your week, and I will see you next week.